Hi everybody, today I'm going to talk about section 6.3 that talks about the Moivre's theorem. And sometimes I'm going to refer it as DM's theorem because it's a little bit of a hard word to say. But pretty much what this theorem is about is how to simplify a complex number that is being raised to a power. And it's actually pretty simple, and hopefully you guys like my proofish. And again, I'm calling it proofish because I'm not going to complete the proof. I'm just going to do a couple of the steps, and you guys will all be able to see a little bit of the pattern. And so pretty much, again, what this theorem says is that if we have a complex number, okay, and so if the complex number is raised to some power n, how does that affect the trigonometric form? And so pretty much what happens is that my modulus, gets raised to a power n. And the other thing that changes is that my theta, my argument, is also going to be raised to the, or it's actually going to be multiplied by that power n. And so my modulus gets raised to a power n, and my argument gets multiplied by this power n. But how did we end up coming up with this really nice little formula here, right? How did we end up coming up with this theorem? So again, I'm going to do a proof-ish. So I'm going to do a couple of different, two different steps, and then we're going to be able to see the pattern. Okay, so pretty much I'm going to show you guys how they came up with that formula. Okay, or how did DM come up with this formula here. And so I'm going to start off with just multiplying by raising z to the second power. Okay, and so again, my z is my complex number, and we're gonna assume that we have it in trigonometric form. And so z squared is the same thing as having z times z. Well, what is z? Well, z, we know that it's r times the quantity cosine of theta plus I sine of theta. And we also know, again, z times z, that means that would we multiply it by itself, so another r times quantity cosine of theta plus I sine of theta. So now I'm just going to use multiplication rules here. Multiplication is commutative, and so we're going to have r times r, and then the quantity cosine of theta plus I sine of theta, and then quantity cosine of theta plus I sine of theta. So r times r, we know that that's r squared. And so I'm going to go ahead and distribute these two binomials. And so we get cosine of theta times cosine of theta, and then plus I cosine of theta sine of theta. And then the next one is plus I sine of theta cosine of theta. Last one, plus I squared sine of theta sine of theta. And we know that we know that I squared is defined to be -1, and so I'm just going to simplify that a little bit here. So cosine of theta, and then I'm going to have negative sine of theta, sine of theta. And again, the reason why I moved it was because I wanted the real parts together and then the imaginary part together. So I get plus I cosine of theta sine of theta plus I sine of theta cosine of theta. And so hopefully you notice that this first part here is actually an identity. This is the cosine of a sum. So this is going to equal to, this here is going to equal to cosine of theta plus theta. Again, this is by an identity. And here, for the second part, if I factor out that I get cosine of theta sine of theta plus cosine of theta sine of theta. And again, that's also an identity. That's the sign of a sum. So here we get cosine of 2 theta plus I, and again this here is, I'm going to do it in pink. This here is also an identity like I mentioned, and this is going to be the sign of a sum. And so this ends up being sine of theta plus theta. Right? And so we simplify this, we get r squared is equal to cosine of 2 theta plus I sine of 2 theta. And isn't that what DM's theorem was saying? Right? If we raise z being our complex number to the power 2, all we're really doing is we're taking the r, our modulus, raising it to that power, and then our angle or argument is being multiplied by that power as well. And so we get z to the second power is just equal to r squared times the quantity cosine of 2 theta plus sine of 2 theta. So again, I haven't generalized this, but you can already see what's happening here. You can already see that again, I call it a proofish because it's not actually proving it in general, but you can see that that it works for z to the second power. Okay. And again, if you really wanted if you really wanted me to get a little bit into it and really do the proof, then just make an appointment with me, and I'll be happy to explain that to you. But I actually wanted to do an example where we actually use this theorem. So let's move on and try an example. So example 1 here tells us use de Moivre's theorem to simplify 1 plus I raised to the 6th power. And again, we have this complex number and now is being raised to the 6th power. And so we don't have to multiply I plus 1 plus I 6 times. We could do that. We totally could do that. But why don't we just use the de Moivre's theorem? It makes our life so much easier, especially because I did a little proofish, so um, we can see that it is true, and it's a proof-ish, but there is a proof out there. And so in order for us to actually use de Moivre's theorem, we actually have to rewrite this complex number in trigonometric form. And so that would be our step 1. So here, I'm just going to write here, I'm going to call this step 1. Write z, which is equal to 1 plus I, that's our complex number, in trig form. And so we have, again, we have my z is equal to 1 plus I. So we have to find our modulus and our argument. So we know that r is equal to the square root of 1 squared plus 1 squared, which is equal to the square root of 2. And I like plotting this. We can always just, I like plotting it, but we could also just use tangent to help us find the angle here. And so this point here, it's going to be in the second quadrant, or actually it's going to be in the first quadrant because they're both positive. So we have positive 1, the real part, and then 1 for the imaginary part. So we're looking for this angle here. I know I wrote it really small. Let me move everything down a little bit from the notes. Looks like we might need a little bit more room. And so here we go. We have, we're looking for tangent theta is equal to 1 over 1. And this is in the first quadrant, so that means that theta has to equal 45 degrees in order for tangent of theta to equal 1. Right? And again, you could have done it a different way. So we have z, this complex number. We already have it in trig form. So z is equal to the square root of 2 times the quantity cosine of 45 degrees plus I sine of 45 degrees. So again, this is just another way of writing 1 plus I, okay, in trigonometric form. And so again, DM's theorem is telling us that if we have a complex number raised to the 6th power, all we have to do is take our modulus, raise it to 6th power, and then take our our argument, which is again our angle, and multiply by whatever that power is. And so let's apply that definition. And so we know, here, let's call that step 2. So we're going to apply the M's theorem. And again, notice that in my power here, my N is equal to 6. So let's actually plug all that into our formula. So we have z to the n power is equal to r to the n power times the quantity cosine of n theta plus I sine of n times theta. So let's all plug everything in. So we have z to the n power, or z to the 6th power actually, is equal to, and we know what r is. R is the square root of 2, so we have the square root of 2 to the 6th power. And then we have cosine times 6 times 45 degrees. And then plus I sine of 6, again, that's my n, and then my theta was 45 degrees. All right. So let's simplify this a little bit. We get z to the 6th power, which again was the original problem. And the square root of 2 to the 6th power, let's actually do that work on the side here. So I'm gonna shade this in pink so I can show you the side work over here. So I'm gonna call this the side work for that part. And so the square root of 2 to the 6th power, that's the same thing as doing the square root of 2 to the 6th power inside of the radical. So the square root of 2 to the 6th power is the same thing as the square root of 2 to the 6th power. And it sounds the same, but the square root of 2 raised to the 6th power is equal to the square root of the quantity 2 to the 6th power. I know it sounds the same, but it's not the same. Okay, and so the square root of 2 to the 6th power is just equal to, you can think about it as, again, this is just going to be the square root of 64, which is just 8. And so here we have 8. Let me stay consistent with the colors here. We have 8 times, and then we have cosine of 270 degrees plus I times sine of 270 degrees. And if we simplify this a little bit further, we get that z to the 6th power is equal to 8 times 0 plus I times -1. Let's make some room here for this work. And again, let's simplify this. So z to the 6th power is just equal to -8I. So hopefully you didn't think that this was too much work. I mean, again, you could have just done 1 plus I, multiply it by itself 6 times, and you would have also got -8I. But again, hopefully you find the M's theorem useful. So that's going to be, again, z to the 6th power is going to be -8I, given that z, my complex number, was 1 plus I. So for the next part, I'm going to talk about how do we take the actual nth root of a complex number. And so again, how do we take the square root or the cube root of a number that is complex? So again, just want to show you guys, give you guys a little bit of intuition why we would need something like this. And so here's a little example, and we're actually going to do this example at the end of this section. So here's an example of when we're going to need it. So suppose that I give you a problem that says x squared plus 2I is equal to 0. And so I'm asking you, what does x have to be in order to satisfy this equation here? So what we could do is again, I could try solving for x. So I have x squared is equal to negative 2i. I take the square root of both sides. So x is equal to plus or minus the square root of negative 2i. Well, how do I actually take the square root of negative 2i? Right? Another way of writing this is x is equal to plus or minus negative 2i to the 1/2 power. That's another way of writing the square root of negative 2i. But again, complex numbers, how do we do it? We know how to do it when we have regular numbers, right? So for example, so this would be example 1. This is actually an intuition of what's going on. So example 2, let's suppose that I tell you, okay, x squared minus 16 is equal to 0. Well, that one we do, again, we try to solve for x, so x squared is equal to 16. And then we get x is equal to, again, we take the square root of both sides, we get plus or minus 16, and that one's not so bad. We're like, okay, well, these are, real numbers. We could either use our calculator, but because 16 is actually a perfect square here, that just ends up being plus or minus 4. But again, we're working with complex numbers, so that's going to be a little bit more of a challenge. That's a little bit of more work. And so that's the next theorem is actually about. And so the theorem is called the nth roots of a complex number. So it's not a very creative title, but again, it talks about if you have a complex number and it's raised to some power, and again, the nth roots, right? It's raised to some power, but these are like this the square root or the cube root. Then how would we actually find? How do we actually evaluate this? And so the theorem says for any positive integer n, the complex number z equals to r, quantity cosine of theta plus I sine of theta, has exactly n distinct n roots given by the expression. And so we're going to get for if we're looking for the nth root, then we're going to get n distinct roots. And so that's going to be given by this expression here. And so what we're going to actually do is we're going to take my r, raise it to the 1/nth power, which is, again, whatever, that would be the nth root. And then we would take the cosine of, or angle, plus 2 pi k, and then divide all that by n. So we're going to take the cosine of that whole thing, that whole expression, plus I sine of that whole expression as well. Right? So again, that's how we're going to be able to generate all of the different solutions, all of the different roots. And here k is defined to equal 0, 1, 2, 3, all the way up to n minus 1. And so again, if n is equal to 5, then my k is going to go up to 4. So it's going to be 0, 1, 2, 3, up to 4. So let me just write that down here. So here, let me expand on this. So if, again, n is equal to 4, then n minus 1 is equal to 3. So k is going to go from 0 to 3. So 0, 1, 2, 3. All right, so again, notice that my n here is 4, so I'm looking for my fourth roots, and so k is going to give me those 4 roots, and that's why we have k being 4 different numbers, k 0, 1, 2, 3, because that's going to generate 4 different roots. Okay, so again, if n is equal to 4, then I'm going to have 4 different values of k that I'm going to plug in. Hopefully that makes sense. If not, I have some examples for us. Okay. So here's the next example. Called it example 2. All right, and so example 2 says find all the fourth roots of the complex number -8 plus 8i square root of 3, and then check by graphing the roots in the complex plane. And I'll talk a little bit about that once we get there. It's a really cool property that it has. Okay, so how do we actually start this? So some of the keywords here is, the keyword here is fourth roots. So they're asking you to find, again, so here, let me write this down. So the fourth roots, like the fourth root of 5, if we write it in if we write it with numbers here, it would be the fourth root of 5. So again, my index here for this radical is 4, so the fourth root of 5. And so, but here we're not looking for the fourth root of 5. We're looking for the fourth root of this complex number. So we're looking for, again, this was an example here, but in our problem, sorry about the cars, you guys. In our problem, we have, we're looking for the fourth root of negative 8 plus 8I square root of 3, which again we could write it as the fourth root of 8, negative 8 plus 8I square root of 3. Oh, yes, square root of 3, which can also be written as negative 8 plus 8I square root of 3 to the power 1/4. And the reason why I wrote it this way is because our formula is written more in that way. Okay, so again, notice that r is raised to 1 over n, which is that root. 1 over 4 would be the fourth root. So again, that's the reason why I'm keeping it this way. So let me just highlight that. So again, 1/4. The reason why I wrote it in that way is because our formula has it in that form as well. And so again, what we're looking for is the fourth roots of this complex number. So let's actually plug things into this formula here that we have from this theorem to actually find all of these roots. And so this is going to take a little bit, just letting you know. All right, but first, before we actually apply this, we have to write it in trigonometric form. So notice again that in the beginning, it talks about z being a complex number and in trigonometric form. So we're going to have to write negative 8 plus 8I square root of 3 in, again, trig form. So let me write that as step 1. Okay, so write z in trig form, which is, again, my z is my complex number. Alrighty. So here we go. We first have to find the modulus. So we have a negative 8 plus 8I square root of 3. My modulus. So we get r is equal to the square root of negative 8 squared plus 8 square root of 3 quantity squared, which is going to give us the square root of 64 plus 64 times 3, the square root of 256, which is going to equal to 16. So we know that r, or modulus here, the distance from the center to that complex number, is 16. Now we have to find the argument, which is again or angle in standard position. And again, notice that my real part is negative, my imaginary part is positive, and so that means that we're going to be in quadrant 2. So again, we have, you can use tangent or you can use sine and cosine. It doesn't matter what you want to use. And so I'm just going to use tangent. So tangent of theta is equal to imaginary part, which is my y here, and then my over my my imaginary part over my real part. And so this is equal to negative square root of 3. And so I'm looking at, okay, what does theta have to be so that tangent of theta is equal to negative square root of 3? And again, this is in the second quadrant because that's where this point is. Okay, this is where the complex number is. And so that means that my theta is going to equal to 120 degrees or 2 pi over 3. And again, it doesn't really matter if you use degrees or radians, since the actual the actual theorem has it in terms of radians. I'm going to be working with radians. It's going to make it a little bit easier to simplify things as well. But you're welcome to use degrees, and instead of having 2 pi, just change it to 360 degrees. It doesn't actually matter. But it's up to you. Let me just, again, we're going to need a little bit more space because I'm actually writing a lot bigger than I thought. So here's step 2. Is to actually plug in the values into my formula. All right, and so we have, again, we have 16. So we have 16 raised to, and again, it was the fourth root, so it's going to be 1 over 4 times the cosine of this giant quantity, which is going to be 2 pi over 3 plus 2 pi k all over n, which was 4, and then plus I sine of the same thing, 2 pi over 3 plus 2 pi k all over 4. So again, this is our formula, and now we're going to plug in values of k. And so again, remember, k ranged from 0 to 3, because that's going to be four different distinct roots. So let's plug in k. I'm going to plug in k equals 0. So we get again 16 to the 1/4 power. That's the same thing as the fourth root of 16, which is just 2. So we're going to have 2, and then here we have cosine of 2 pi over 3. And again, since k is equal to 0, that 2 pi goes away, and we just divide this by 4. I sine of, again, the same thing, 2 pi over 3 divided by 4. So I'm going to simplify that. Let me just leave this here. Okay, so I get 2, so this equals to 2 cosine of 2 pi over 12 plus I sine of 2 pi over 12, which is the same thing as pi over 6. And so this is going to equal to 2. And then cosine of pi over 6 is just the square root of 3 over 2. And again, sine of pi over 6 is just going to be 1/2. And so if I distribute that 2 in there, I get the square root of 3 plus I. And so that's going to be one of the roots. Okay, so when we take the fourth root of that complex number that we started originally, one of those roots is going to be square root of 3 plus I. Now let's plug in k equals 1. So this is going to be 2 cosine of 2 pi over 3 plus 2 pi. So now we actually have that 2 pi all over 4 plus I sine of, again, 2 pi over 3 plus 2 pi all over 4. So here we do have to simplify a little bit. So this simplifies to cosine of 2 pi over, sorry, no, not 2 pi over 3. This simplifies to 2 pi over 3, which is what I had said originally, times plus I sine of 2 pi over 3. And so we get 2, and again, cosine of 2 pi over 3 is negative 1/2. And then sine of 2 pi over 3 is the square root of 3 over 2. So if we, again, I'm going to need a little bit more space here. A lot more space. So let me just push that down a little bit. So here this is going to equal to -1 plus I square root of 3. So again, that's the other root. And so again, we still have to do k equals 2 and then k equals 3. So it's a little bit of work here. So k is equal to 2. We have again 2 times cosine of 2 pi over 3 plus 2 pi times 2 all over 4 plus I sine of 2 pi over 3 plus 2 pi times 2, which is just, again, 4 pi here, all over 4. And if we simplify this, we get 2 cosine of 10 degrees, which is the same thing as 7 pi over 6, plus I sine of 7 pi over 6. And again, 2 times cosine of 7 pi over 6, that's just equal to negative square root of 3 over 2. And then I sine of 7 pi over 6, it's going to be negative 1/2. So this just simplifies to negative square root of 3 minus I. So again, that's the other root. And for our last root here, so here we're going to do k, change the color here. K is equal to 3. That's the last root. And so we're going to have 2 times the quantity, cosine of the quantity 2 pi over 3 plus 2 pi times 3 all over 4 plus I sine of 2 pi over 3 plus 2 pi times 3 all over 4. If we simplify this a little bit, we get the cosine of 5 pi over 3 plus I sine of 5 pi over 3. Simplify this a little bit, we get cosine of 1/2, cosine of 5 pi over 3 is 1/2, and then sine of 5 pi over 3 is negative square root of 3 over 2. So again, if we simplify that, we get 1 minus the square root of 3 times I. So we have our 4 different roots. So I'm going to write all of them down here. So the fourth roots of negative 8 plus 8I square root of 3 are, so we had square root of 3 plus I. We also had negative 1 plus I square root of 3, negative square root of 3 minus I, and last one is 1 minus I square root of 3. And so remember I told you guys to check by graphing the roots in the complex plane. So let's actually do that. Right, so here's my little my complex plane here. So I'm gonna graph these 4 solutions here, and I just want to show you guys that there's something really cool that's happening here, that when we graph the complex roots on the plane, you're gonna see that there's some really cool symmetry, or really cool let me just graph them here and then we'll talk about it. So the square root of 3 plus I, well, the square root of 3 is approximately 1.732 something. And so let me just, again, it's not going to be very accurate, but again, I just want to talk a little bit about it. And so here are my solutions here. Let's do that in let's just this cool green. Actually, I already have that green over here, so let's maybe just choose it. So square root of 3 plus I, and again, this is gonna be my real axis, and this is my imaginary axis. And so my real part is the square root of 3. So the square root of 3 again is approximately 1.73. So that's going to be somewhere over here. And then my imaginary part is 1. So here's going to be, I'm going to call this one A. So this is going to be my A. And then my B, again, this is going to be B. This is going to be C. And this is going to be D. So my B is going to be -1 is the real part. And my imaginary part is square root of 3. So that's going to be somewhere right here. And then negative square root of 3 minus I, that's going to be uh, real part is negative square root of 3, and imaginary part is -1, so that's somewhere right here. That's C. And then D here is going to be 1 minus I square root of 3, so real part is 1, and then imaginary part is negative square root of 3, so that's somewhere down here. And again, it's not drawn to scale, but the really cool thing about this is that the solutions, your roots are going to be equal distance from each other. So they're, when you graph them, they're going to be, again, A is going to be equal distance from B, B from C, C from D. So again, if you see that A and D are way too close to each other and they don't look like they're the same distance around from everybody else, then you know that you did a mistake in when you plugged everything in. So that's a cool way to figure out if you actually if you actually use that theorem correctly. When you graph the solutions, they have to be equal distance from each other. Okay, so they have to be equally spaced, and it's easier to see it if you actually draw a circle. You're going to be able to see that they're equally spaced. So it's a little bit hard here because, again, it's not drawn to scale, but again, I did want to talk about that.